Here's a mind-blowing fact for you. Chile has the technical capacity to generate renewable energy, something like 100 times greater than its current needs.
100 times. It's huge.
Exactly. Yet today, a full two-thirds of its energy still comes from, well, digging up or piping in fossil fuels. It really makes you stop and think, doesn't it? Are we, globally truly embracing the clean energy revolution that science says is possible? Or are we maybe stuck in old ways of thinking?
That's really the core question.
And that's the central question we're diving into today.
And to help us explore that, we're really digging into the findings of a specific study. It's titled, Insights for Informing Energy Transition Policies. Are Decision Makers Listening to Science? The case of Chile.
Okay.
This research, it meticulously examines the gap between the energy transition policies governments are putting in place, and while the pathways that scientific research indicates are not only necessary, but actually achievable to meet our critical climate goals.
And Chile is such an interesting case study here, isn't it? Because they have actually made pretty significant strides in deploying renewable energy.
They have, yeah. It's not like they're ignoring it.
Right, which actually makes the discrepancies this study points out even more stark, I suppose.
Precisely. Our aim in this deep dive is really to give you a clear picture of the most significant obstacles holding back a faster energy transition.
Using Chile as the example.
Exactly. By focusing on Chile through the lens of this study, we can pull out some valuable insights that probably apply elsewhere, too. Ultimately, it shows us how we might bridge that really crucial divide between, say, ambition and actual action.
Okay, so let's set the scene first. What does Chile's energy landscape actually look like right now, according to this study?
Well, as you mentioned, they're heavily reliant on fossil fuels. We're talking oil, coal, natural gas. Back in 2021, that made up around 65% of their total primary energy supply.
65%, wow.
Yeah, and this dependence, it fuels pretty much everything: cars, trucks, power plants, industry, even heating homes and businesses.
And does the study break down where those fuels are used? Like, is it mainly electricity or?
It does. It's quite interesting. For example, transportation just dominates oil consumption. Nearly 60% of all oil goes there.
Okay.
Coal, on the other hand, is almost entirely for electricity generation, something like 97%.
Right.
Natural gas is a bit more mixed. About 60% goes to electricity, but significant amounts are also used in industry and for heating buildings.
But like we said, it's not all fossil fuels. They have seen some really impressive growth in renewables, particularly electricity.
Absolutely.
The study calls most of these non-conventional renewable energy, or NCRE. Can you just quickly clarify what NCRE usually includes?
Sure. Generally, that means renewables other than the big traditional hydropower dams. So things solar, wind, geothermal energy, that kind of thing.
Gotcha.
The figures for NCRE in Chile from 2022 are actually quite striking. Electricity generation from these sources, it blew past the legal targets. Yeah. Renewables accounted for a third of the country's total electricity consumption that year, and they added a record amount of new NCRE capacity, 2.56 gigawatts. That's about a 30% growth rate in just 1 year.
That's huge.
And here's a big milestone. The combined electricity from solar PV, concentrated solar, and wind actually generated more power than coal-fired plants for the first time ever in 2022.
Okay, that sounds like genuinely fantastic progress.
Oh.
But I sense a but coming. The study talks about a significant increase in something called curtailment of solar and wind. What's that about?
Oh, yes, curtailment. This raises a really important point about, well, system efficiency. Basically, curtailment means perfectly good. Clean energy that's already generated has to be deliberately cut back or just dumped because the grid can't handle it at that moment.
So you're literally wasting clean energy.
Pretty much. And this study explains why. It points to several key factors. Not enough capacity in the transmission lines to move the power where it's needed.
Okay, bottlenecks.
Right. A lack of sufficient energy storage, think batteries. Also, outdated policies for managing the grid itself and limited demand-side management.
Demand-side management. What does that involve?
That's about finding smart ways to shift when energy is used. For example, encouraging people to charge electric vehicles when solar power is abundant instead of during peak evening hours.
I see.
And the last factor mentioned is a lack of sector coupling infrastructure.
Sector coupling. Okay, that sounds important. Let's unpack that a bit. What does sector coupling mean here?
Right. Think of it as smartly linking different parts of the energy system that are usually separate, like the electricity sector, the heating sector, and the transportation sector.
How would that work in practice?
Well, for instance, if you have excess renewable electricity, instead of curtailing it, you could use it to produce green hydrogen through electrolysis. That's often called power to X, or PTX.
Okay.
And that hydrogen could then be used as clean fuel for trucks, ships, or in industrial processes that are hard to electrify directly.
Ah, so it connects the power sector to other energy uses.
Exactly. This study argues that because Chile lacks this kind of integrated approach, along with those other issues like transmission and storage, they're missing a major opportunity to really capitalize on their massive renewable potential, not just for their own use, but even for exporting clean energy products.
And it's not just about the big utility scale stuff, right? This study also mentions individuals, prosumers, people with solar panels on their roofs.
That's right, prosumers producing and consuming. Even though Chile has rules for net billing, which lets people sell excess solar power back to the grid, the actual uptake has been pretty slow.
Why is that?
Well, this study highlights several hurdles, things like the high initial cost of installing solar panels.
Always a factor.
Yeah. Also, a lack of really strong financial incentives to encourage it, some regulations that are a bit too rigid about system size, and just long, complicated paperwork processes.
So it feels like the raw potential is definitely there, but the system, the grid, the markets, the rules isn't quite keeping up, both at the big scale and for individuals.
That sums it up pretty well. This study also hammers home Chile's reliance on energy imports a huge 65%, which of course ties back to fossil fuels since
Right.
they don't have large reserves of their own.
Right.
And another point is how compartmentalized their energy system is. Different sectors don't interact much, which hinders flexibility and overall efficiency. What's really striking, though, is that the study points out that the scientific community has understood these core problems: the fossil fuel dependence, the import reliance, the lack of integration for, well, over a decade.
A decade.
Yeah. And on top of that, the official government energy plans often seem to overlook some really significant side benefits of a faster transition, like cleaner air leading to better public health, or the potential for creating lots of new jobs.
Okay, this really sets the stage for digging into Chile's actual energy transition policies then. Where do they start, and what are the current targets they've set?
Well, Chile's had energy policies for a while, but the real push towards these non-conventional renewables, the NCRE, kind of kicked off around 2008. But it wasn't until 2015 that they set up their first proper long-term energy policy. The headline target back then was getting to at least 70% renewable electricity by 2050.
70% by 2050. Okay. And this study mentions a regular review process, the PLP, the Long-Term Energy Plan.
That's right, the PLP. It's designed to be a participatory process involving different stakeholders, and it's meant to adapt to new technologies and changing priorities over time.
Sounds sensible.
The first PLP report came out in 2018, looking ahead to 2046. Since then, they've had annual updates, which led to a big revision of the National Energy Policy in 2022, and a new PLP report that same year.
So what are the updated goals? Have they gotten more ambitious?
Oh, definitely. The updated policy and the latest PLP are much more ambitious. They're now aiming for 80% renewable electricity by 2030.
80% by 2030. Okay.
100% zero-emission electricity by 2050, and cutting greenhouse gas emissions from the energy sector by 60% by 2050 compared to 2018 levels.
That's a significant step up.
It is. And the very latest PLLP scenarios even talk about phasing out coal power completely by 2035 and achieving overall carbon neutrality for the whole country by 2050. There's even an accelerated transition scenario that pushes the coal phase out to 2030.
Wow. Okay, that sounds really impressive on paper. And yet, this study still seems critical. It mentions these policies are rated insufficient by the Climate Action Tracker and aren't aligned with the 1.5-degree warming limit. Why would that be if the targets sound so good?
Yeah, that's the million-dollar question, isn't it? It really comes down to the underlying assumptions and maybe the scope of the plans. This study points out that even with these updated targets, the current official plans still anticipate using a significant amount of fossil fuels in 2050.
Still, even with 100% zero-emission electricity.
Well, remember, electricity is only part of the energy picture. You still have transport, industry, heating. And the plans also seem to rely quite heavily on carbon dioxide removal technologies down the line, which, are still pretty uncertain in terms of effectiveness and scalability.
Okay. So it's not fully decarbonized across the board.
Exactly. And what's really interesting is that this study highlights that scientific research has been outlining potential pathways for a completely defossilized energy transition in Chile for several years now. These studies existed even before that first PEL-P report in 2018.
So science was already pointing to a 100% renewable future back then.
Yeah.
What kind of timelines were those studies suggesting?
Many of them, going back to around 2017, showed it was technically and economically feasible to get to a 100% renewable electricity system by 2030 or 2050.
Right, the power sector first.
Yes, and a common thread in these studies was the crucial role of decentralized systems, especially getting lots of solar PV onto homes and businesses, those prosumers we talked about. Then, more recent studies focusing specifically on Chile's entire energy system concluded that full defossilization across all sectors is possible by 2050, maybe even earlier. Some research even suggested Chile could hit carbon neutrality as early as 2030.
2030, that's incredibly ambitious compared to the official 2050 goal.
It is, and get this. This study even mentions research indicating that going for that fully defossilized pathway could actually end up being cheaper than the government's current target path from about 2035 onwards.
Cheaper, really.
Yeah.
That's counterintuitive for many people, I think.
It often is, but the falling costs of renewables are changing the game. And the benefits aren't just climate-related. According to the study, a fully defossilized system could create around 350,000 more direct jobs in the energy sector compared to the government's current 2050 carbon neutrality plan.
More jobs and potentially lower costs later on. So if the science paints this picture faster, maybe cheaper, more jobs, why isn't it fully reflected in Chile's official energy planning, the PLLP?
This study points to some specific weaknesses, right? Exactly. It boils down to, basically, the tools and assumptions used in the official planning. This study identifies three main shortcomings in the modeling used for the PLP. First, low temporal resolution.
Temporal resolution, what does that mean?
It means how finely they slice up the year when they run their energy system models.
Yeah.
Historically, the PLP used incredibly few time slices, initially just 8 for the whole year.
8. For 8 times 760 hours.
Crazy, right? It's improved now to 288 hours in the latest version, which represents different times across the year, but that's still way less detailed than many scientific studies which use the full hourly resolution, all 8,760 hours.
Why does looking at every single hour matter so much? It sounds like a lot more work.
It's absolutely crucial, especially when you're dealing with variable renewables like solar and wind. Think about it. Using just a few typical days makes it really hard to capture the real-world hour-by-hour interaction between solar output and wind output.
You miss the fluctuation.
Precisely. You can't accurately model the balancing needs across different seasons or plan for those critical periods, sometimes called dark doldrums, when you might have low sun and low wind for several days.
Ah, the worst case scenarios.
Exactly. Relying on simplified time resolution just doesn't cut it for planning complex, modern, renewable, heavy energy systems. The scientific literature has been saying this for years. It's kind of an outdated approach.
Okay, that makes sense. So underestimating the variability could lead to underplanning for things like storage. What was the second weakness? Cost projections.
Yes, overly pessimistic, or perhaps just outdated cost projections, especially for solar PV.
Solar being key for Chile, obviously.
Hugely important. This study found that the cost assumptions used in the PLP for large utility-scale solar farms, even looking ahead to 2030, were actually higher than the lowest real-world costs achieved in Chile back in 2022.
Higher than costs already achieved years earlier.
Yes, and looking further out, the PLP's projected costs for solar TV from 2030 to 2050 are way higher, between 1.4 and 3.7 times higher than other benchmarks, like optimistic projections for rooftop solar in Chile, recent scientific findings for utility PV there, and even projections for large-scale solar in Europe.
Wow, that is a massive difference. How does using such high cost numbers affect the planning outcomes?
Well, it directly makes renewable energy look less economically attractive in the models compared to other options.
Like fossil fuels, or perhaps nuclear or imports.
Potentially, yes. It skews the results. It leads the models to underestimate the optimal amount of renewables that should be built, and it distorts the perceived cost-effectiveness of other clean solutions like Power-to-X and that sector coupling we talked about.
Okay, so inaccurate time slices and inflated renewable costs. What was the third key weakness the study identified?
That was the partial modeling or sometimes complete absence of key enabling technologies and infrastructure.
Enabling technologies, like what?
Things like Power-to-X for making e-fuels, the whole concept of sector coupling itself, and also technologies like district heating systems. These are all crucial for a few reasons. They help replace fossil fuels in those tricky sectors like heavy industry or shipping.
The hard-to-abate sectors.
Exactly. They also add flexibility and resilience to the whole energy system and improve overall efficiency. Think of concepts like smart energy systems or multi-energy systems. That's what the science talks about.
And the PLP models weren't fully capturing these.
Apparently not sufficiently. By not fully modeling these technologies, the planning misses out on understanding their potential. Their potential to provide flexibility, to meet future demands for things like e-fuels, to use the flexibility of future tech like electrolyzers or EV charging smartly, and to find synergies like building hydrogen hubs that serve multiple industries.
It feels like leaving these out could really lock Chile into pathways that aren't the best or the cheapest or the fastest for decarbonization.
That's the argument this study makes. And it also briefly notes the need for more research into demand-side management and really exploring that export potential for power-to-X products.
Right, the e-fuels, e-ammonia.
Exactly. Chile's got amazing conditions for making this stuff e-methanol, even e-plastics, potentially creating a whole new export industry. But if your planning tools don't properly account for these possibilities, you won't develop strategies to capture that opportunity.
So let's circle back to the big question in the study's title. Are decision makers listening to science? Based on everything we've discussed about Chile, what's the verdict from this study?
Well, based on the evidence presented here, it seems Chile's situation is unfortunately pretty typical.
Oh, really? Not unique.
Apparently not. Many countries have strong scientific research showing 100% renewable pathways are possible, but very few governments have fully adopted that vision in their official policies. Denmark is mentioned as maybe the only one that has really gone all in so far. The common weaknesses we talked about, low temporal resolution, pessimistic costs, underrepresenting key tech, these seem to be persistent problems in official energy planning globally, even though science has been flagging them for years.
And are there concrete signs of this disconnect in Chile?
This study points to tangible metrics, things like the increasing amount of renewable energy being curtailed wasted, essentially, and the fact that their dependence on imported energy remains stubbornly high. These are seen as real-world indicators that policy isn't keeping pace with the potential.
So the conclusion is?
The study concludes that valuable insights from scientific expertise, particularly in energy system modeling, haven't been fully integrated into the policymaking process. And this failure to listen is ultimately hindering the speed and scale of the energy transition that's needed.
Which is concerning, given the urgency of climate change. Does the study mention any limitations of its own analysis?
Yes, briefly. It acknowledges it focused mainly on techno-economic comparisons. And because of the data available in the studies it reviewed, the cost comparison really zoomed in on solar PV.
So more research could look broader.
Definitely. Future work could dig deeper into other environmental impacts or wider socioeconomic factors beyond just emissions and direct energy jobs.
Okay, so bringing this all together, what's the absolute core message you think listeners should take away from our deep dive into this study? Insights for informing energy transition policies. Are decision makers listening to science? The case of Chile.
I think the main takeaway is this. There's a significant and frankly worrying gap between what Chile's current energy policies aim for and what scientific research shows is actually achievable and potentially better for their energy transition.
And this gap isn't just theoretical. It stems from using outdated modeling tools and assumptions in their official planning.
Exactly. Tools that tend to underestimate the potential and cost-effectiveness of renewables and overlook crucial enabling technologies that could accelerate the shift away from fossil fuels.
So, what should be done? What are the key recommendations this study makes, especially for policymakers, regulators, planners, investors, particularly as Chile apparently has another update to its long-term energy plan coming up?
This study lays out several clear recommendations. First, seriously consider the findings from scientific research when setting policy targets. Don't just stick to incremental improvements.
Look at the 100% RE scenarios.
Right. Second, adopt state-of-the-art modeling tools. That means using full hourly resolution.
All 8,760 hours.
Yes. Third, use up-to-date, realistic cost projections for renewables, not figures that are years out of date or overly pessimistic.
Makes sense.
Fourth, fully integrate those key enabling technologies, decentralized solar sector coupling via Power-to-X, into the models. Don't leave them out or underestimate them.
Okay.
Fifth, actively explore demand-side management strategies. Sixth, properly analyze the potential impacts of making renewable-based power-to-X products, both for Chile's own use and for export.
The solar-to-X economy idea.
Exactly. And finally, seventh, make sure to consider the broader benefits beyond just emissions, things like public health improvements and job creation in related industries.
It really highlights that there's so much potential being left on the table, isn't it? That idea of Chile becoming a leader in a solar-to-X economy is quite powerful.
It really is. Chile has this incredible endowment of renewable resources. They genuinely have an opportunity to build a new era of prosperity based on clean energy and power-to-X products. But as the study emphasizes, actually realizing that potential hinges on embracing energy strategies that are grounded in the best available science.
And the lessons here aren't just for Chile, presumably.
Not at all. The issues raise the modeling weaknesses. The gap between science and policy are relevant almost everywhere. The analytical framework used in this study could easily be applied in other countries or by international bodies trying to figure out how to accelerate a just and effective energy transition.
A really fascinating and slightly sobering deep dive. The study we've been unpacking today, once again, is titled Insights for Informing Energy Transition Policies. Are decision makers listening to science? The case of Chile.